Hello, my name is Lindsay August. This is my technical presentation for engineering statistics, and I'm going to be talking about z-testing. Z-testing is a kind of hypothesis testing where we are putting out a null hypothesis and doing different calculations to determine whether we can accept or reject that null hypothesis, but never able to prove that it's true. And we can do a right-tailed z-test, left-tailed, two-tailed, proportion testing, single sample, multi-sample, and I'll get into those in a little bit. And I chose this topic because I am a manufacturing support member at Lockheed Martin, and some of the work that we do is looking at inventory health based on taking a sample of a certain kind of material in a certain location off a certain machine, etc., and doing tests on it to determine whether that material is living up to certain values that we expect. And so I was really interested in looking more into it through this project. The theory behind z-test, there are, again, all of those different variations. If I'm looking at a right-tailed test, I'm looking at relationships more towards the higher values, towards the right side. The left tail is the opposite, and two-tail is across the board. And then central limit theory is the basics or the background of a lot of different statistical analysis, but it definitely has its application towards z-tests, which assume that a large enough sample will follow a normal distribution. And again, we can never prove our null hypothesis, but we're putting it out there to see if we need to reject it. And then the reason we might want a z-test versus a t-test is because we're working with a larger sample size, and over a chi-square test because we're not working with as categorized data or like as many sources. So looking at the formulas, they're similar but not the same for different kinds of z-tests. You're looking at your x bar, your sample mean, your mu there is your population mean, and sigma is the population standard deviation. And this formula can be altered where we don't need a population standard deviation or population mean, but can look at sample values versus our expected that we would use as our population mean. And then when we're doing multiple samples, we need to take into account the sample size, n, or the number of observations we're making. And then when doing a proportion test, we need to compare values, and we do that with the variance, our standard deviation squared on the bottom there, over the number of observations added to the same for our second sample, and all square rooted versus the means, the difference between the means. And these are giving us our test statistic, and we have a confidence range. If my alpha is 0.05, then if my z-score is not within the range of negative 1.96 to 1.96, I'm going to reject it. So that's one example. And my example is, again, I work in a case like this, so a machine that is supposed to create a bolt with a 3 centimeter diameter. If we take a population and we want a larger population, otherwise we'd want a z-test, so larger than 30 normally. So let's say I take 50 bolts and I assume that my population mean is going to be 3 centimeters. That's my null hypothesis, so that's my test value. And I take the 50 bolts, I measure them, so I get my sample mean and my sample standard deviation from my measurements. Then I can find my z-test statistic with the formulas on the previous slide, and then see if they fall within my confidence range, the z values. And if they don't, I reject my null hypothesis that no, the values coming off of the machine are not within the range that I want them to be. So I'm going to need to look at doing repairs or creating a new piece of equipment there in this example. And that is everything I have. I have really appreciated this class and getting to learn and connect more to some of the work that I've been doing and will continue to do. So thank you so much.